Hello guys, welcome to my YouTube channel. Today we are going to see what's Rust and what are the advantages and disadvantages of Rust, and what are the advantages it's going to bring when we are running the Rust in embedded systems. So first of all, what is Rust? Rust is a advanced system programming language focused on safety and performance, and it has memory safe design and no garbage collectors, which means there will be no problem with dangling point errors or uh, undefined pointers accessing problems. Perfect for embedded and OS development and any performance critical systems. And what are the applications of Rust? There are multiple applications of Rust, one of which is embedded systems, and the other one is web development. Recently, there are a lot of development in web using Rust, and uh, there is network programming and blockchain development. And what are the advantages of Rust, and why we are using it in embedded systems? So, memory safety without garbage collector, which means no null point dereferencing, or after free the pointer will get uh, completely out of the scope and we can't access it, and there won't be any errors even if we have access like that, and it will throw errors before come even running. And zero cost abstraction means uh, there is no extra cycles that are taken by Rust when we are using Rust specific components, and um, when we convert this into a mission level code, then there won't be any uh, extra uh, RAM allocation or anything. So we can directly use it, and it is gives the same performance as of C, and it has strong type system, and because of that it catches bugs easily, and there won't be any issues with bugs in the runtime, and everything will be caught in the compile time itself. And we have concurrency, which means multi-threading, and easy package manager using Cargo and Craze.io. You can find this Cargo and Craze.io in the official website of Crates.io. And what are the disadvantages of Rust in embedded system? So, Rust is a new programming language, so you will be having a steep learning curve, and in this you will be having new concepts like ownership, lifetimes, and borrow checker. Uh, and this can be quite tough to understand initially, but once you get the hang of it, it will be quite easy. And toolchain maturity, not all MCUs and all chipsets are giving support to Rust, and it is temporary for now, but in the future everyone will come up with their own Rust support packages, and it will be quite easier in the future. And lack of legacy libraries, unlike C, Rust embedded system is still growing, so um, we won't be having legacy libraries like the old libraries which are inside C, but we can still use C programming language, and use them, call them in the Rust, and use them. And debugging tools are still not yet developed completely for the C, but completely for the Rust, but there are still developing, but there are still developing, and in the future everyone will be every debugging component will be providing support for Rust also. And why is Rust for embedded system? As you can see in the embedded system, you may find situations like where there will be a lot of problems with data race conditions, and um, um, free pointer access problem like dangling pointer error and everything. So in Rust, it has been taken care by memory safety compiling with the core concepts like ownership and borrowing, and zero cost abstraction, as it is not going to take any extra uh, memory or cycles for building. It is it gives the same mission code as of you are using seed, and we have built-in concurrency, which will uh, give us output without race conditions. And modern tooling, like we have a lot of packages in Rust, and those are all managed by using cargoes and grids. And the first core concept is ownership. So, when you declare a variable in a function, then the owner of the variable will be the function itself, and you can only transfer the ownership to another variable in the function. But once you have done that transferring, you cannot have the access to that first variable. As you can see in this example, uh, this one has been declared, and it has um, the ownership to hello, and S1 ownership has been given to S2. So that means the S2 is having the ownership right now, and we can print the value of S2 by using the println function. And if you try to print the S1 function, S1 variable using print, you can't. It throws some error stating that you're trying to access the ownership of another variable. So keep in mind that uh, putting equal to doesn't mean you're copying the value, you're giving the ownership right away. And we have immutable borrowing. So immutable borrowing says that you can give the value of a variable by giving the reference using ampersand s1. And here in this example, you are giving it by ampersand s1 to calculate length function. In this, it can only read the values and cannot change the value of s1. Uh, and because of that, if you try to change it in the inside calculate length function, you can't. You will be getting a compile time error stating that you're trying to change, so it can't be accessed in the calculate length function. So, and the next concept is mutable borrowing. So, mutable borrowing, the previous one was immutable borrowing. Now we can give the access of writing the give the access to write the value inside the variable. That means by giving ampersand mute s value to append world, we are giving the write access to the s value. We are giving write access to the s value to the append world function. By that, it can add hello world after hello, and you can if you try to print this s, you can find hello world has been print. In this, there is a violation of mutable and immutable uh, borrowing. So once you have declared immutable borrowing, you cannot declare immutable borrowing. That means if you are giving borrowing to any variable, it has to be either mutable or immutable. If you are giving it as mutable, you can't give it to multiple variables because it can cause data race conditions. And if you are giving immutable borrowing, then you can give it to multiple values, and either of them can not cannot change the value. So multiple immutable reference can be given, and you can see the let r3 with ampersand mute s cannot be run. It will comes up with an error if you try to execute this line. And the fourth one is lifetimes. In C, you usually use pointers with memory allocation, and after memory allocation, you're going to use free function to uh, deallocate all the memory. Whereas in Rust, you can use lifetimes concept, where once you're done with usage of any variable, you can clear the data of the variable. Uh, and it is taken care by the Rust program itself, so you don't need to worry about giving free function and erasing the data. So as you can see in the function, we have longest function with um, dash a as a lifetime, and we have x and y as input, which is also having dash a as lifetime, and we'll be having a output with dash a as uh, output. And in this uh, dash a means lifetime. Once any of the lifetime of x and y, if either of x and y's lifetime is finished, then the lifetime of the output will also be removed. That means you cannot access the data of x and y outside the scope of the function. So here you can see the longest is given with the immutable reference s1 and s2, and both are having a lifetime of dash a. So here we have S1's lifetime and S2. If the lifetime of S1, that means if you are um, if you are calling this function outside of where S1 and S2 are defined, then you might face the problem of lifetime, that the output has been uh, invalid. So I hope you understand the concept here. That means the output of uh, the output variable's lifetime depends on the inputs variable, and as you are giving x and y as the which are inputs, you are giving the same values as output. So the outputs lifetime depends on the inputs lifetime. So this is an embedded Rust code example for blinking LED. So in this example code for blinking LED in Rust, now I'm going to explain you line by line. So the first one is hashtag no std. That means no standard libraries are included. And the second one is no main. The no main tells the uh, Rust that uh, there is no entry point at the main function. Usually, whenever if code runs, the main entry point will be main, and by giving no main, it removes the main entry point, and we can declare the our custom entry point. Here you can see use cortex mrt entry is where we are giving entry point to the function, and this is the this is import of this is an import from cortex mrt, and we are importing entry. And this is import from stm32 f4 hall package, which will have peripheral details like pack and prelude, and inside prelude we are importing everything by using asterisk. And hashtag entry main is where the entry point of the function has been defined. And after entering the function, we are defining a variable named dp. uh, a variable is can be defined using let keyword. Let dp is equals to pack peripherals, and inside peripherals we are calling a function take and unwrap. Take will give out all the peripherals that are present, and unwrap will um, make sure that take doesn't give out any errors. Unwrap will make sure if any panic halts happen, it will catch. And the next one is let rcc. So rcc means reset clock control, and we are just using this RCC constraint by calling the constraint, and we'll be using RCC uh, for resetting the board when something happens. But in this example, we're not going to use it anywhere. And we have GPIO PA. This GPIO PA is taking data from DP variable that we are declared, and inside GP we are taking GPIOA peripherals, and using split function, it is going to split all the peripherals and pins that are present to the GPIO PA variable. And in the GPIO PA variable with PA in with PA5, this is a LED LED's uh, address name. Uh, you can find this in the STM32F4 board packages in Rust in Google. You can search for them. You can find all the documentation regarding that. And in PA5, we are calling into push pull output. This will give out the LED's address to the LED variable here. And we are, as you can see here, we are using mute, which means it can be mutable, as we are using LED toggle inside the loop function. We will be using mute. Inside loop function, we are using LED toggle to turn the LED on and off. And Cortex M4 ASM delay will give out a delay of uh, the Cortex M ASM delay will delay the mm, LED blink toggle for um, 8 0 0 0 0 cycles. The value which we are giving is the number of cycles that it's going to delay for. And you can change it by this is going to delay for 1 second. You can change it by giving the cycles that are required. This cycles are dependent on the clock cycle of the board that we are using. And that's it about this example. And you can try this. I'm going to show this example being run on a physical board later in the next video. And uh, stay tuned and subscribe to the channel to so that you can uh, get intimation when I post the video on how to implement this Rust function in Embedded C and toggle LED. And so let's recap the concept that we have covered in this video. The first one is ownership, and how the ownership of a variable is can be transferred, and how the reference can be given. And the next one is borrowing. Borrowing, how we can safely give the value with read and write concepts, and by giving mutability, we can give the right access to the variables. And lifetime, which prevents invalid references, and um, deallocates the memory once it's done with the usage. So that's it for today's video. I hope you got a clean idea of Rust. If you're not clear with any concept, please let me know down in the comments so that I can help you out and uh, make a clear understanding of Rust. uh, and please make sure to like, share and subscribe to my channel. Thank you very much for watching the video.